San Francisco, 1906. One of the first motion picture cameras records the aftermath of a major earthquake. Hundreds are dead, and virtually every building and house in the center city destroyed. Mount St. Helens in Washington state erupts with devastating force. In a matter of seconds, a mountain disintegrates into smoke and ash. In addition to the human loss, tens of thousands of animals, trees, and plants are destroyed. Today in Hawaii, molten rock erupts from the earth in fiery display. Farms, villages, and forests are destroyed. Seemingly unrelated, these catastrophes have much in common and serve as a reminder that our Earth is perpetually changing. To understand why and how, we have to go back hundreds of years. When the first maps of the complete world were charted and drawn 400 years ago, they revealed some remarkable oddities. In 1620, the English philosopher Francis Bacon was among the first people to comment on what he observed.
If you were to take South America and somehow uproot it, pushing it across the Atlantic, you would find its shoreline matches that of Africa's with startling accuracy. Why, it's as if there were two pieces of one continent that had somehow drifted apart.
Bacon also noted similarities with other continents. North America, for example, made a near-perfect fit with the northern shoreline of Africa. Yet few people took Bacon's ideas seriously.
Have you heard the latest from Sir Francis?
You mean the drifting continents?
Indeed.
I think the poor chap has been working too hard.
The idea of drifting continents would be forgotten for nearly 300 years. Then in 1912, Alfred Wegener, a German scientist, presented his view of continental drift.
At one time, all of the continents were one. It was a giant supercontinent. I call this supercontinent Pangaea. Then, because of forces deep within the Earth, the continents began to move apart and over millions of years arrived at their present positions.
If Wegener's theory were correct, it would certainly explain many of the mysteries that troubled scientists of the day. They had wondered why many life forms in South America, lemurs for example, were virtually identical to those in Africa, when both continents are separated by thousands of miles of ocean. The lemurs are similar because they spread from Africa to South America before the continents broke apart. But Wegener was unable to explain how continents could move.
It's ridiculous, this whole idea of moving continents. What force could possibly move entire continents?
Wegener's idea of a supercontinent would not be taken seriously until startling new evidence came to light. They were just rocks, volcanic debris, but within them was the evidence that proved continents had to move. Millions of years ago, rocks like this were in liquid form, known as lava. As the lava cooled, the magnetic minerals within it, iron particles for example, oriented themselves or pointed in the direction of magnetic north. The minerals were drawn to the north in much the same way that a compass needle is drawn to the north. But what scientists were to discover was that the older rocks, those that were many millions of years old, did not align themselves with magnetic north. Mineral alignments in ancient rocks found in several areas of California should have pointed in this direction, magnetic north. Instead, they all pointed this direction. Rock samples taken from throughout the world presented similar mysteries. Most of the rocks pointed in wrong directions. There was no way to explain it until the idea of drifting continents came to mind. When the continents are repositioned into their original supercontinent, the arrows no longer point in the wrong direction. They all point where they should point, magnetic north. How is it that entire continents move? To find out, we have to look deep inside the Earth. The Earth's core is composed of solid rock, surrounded by hot, liquefied rock, or magma, which is surrounded by another layer of magma slightly cooler than the one below it. Magma is similar to lava that flows from volcanoes, except magma is even hotter and thicker than lava. The outermost layer of magma is called the mantle. Directly above the mantle is the Earth's thin shell. The shell is composed of rock that is cracked into giant slabs, referred to as tectonic plates. Embedded within these plates are the continents and ocean basins of the world. This map shows the Earth's shell where it is broken into 7 major plates and some minor ones. Each plate carries a continent, or a part of a continent, or an ocean basin, or part of an ocean basin. The position of these plates is only temporary. They are moving at an average rate of about 2 inches a year in a variety of directions. We can't see the movement, but we can see the effects. Earthquakes and volcanic eruptions are just 2 dramatic effects of plate movement. Here's why the plates are moving. This is a cross-section of the North American plate on the left and the Eurasian plate on the right. The depression between the two is the Atlantic Ocean basin. Scientists have discovered that hot magma from the Earth's mantle is squeezing up between these 2 plates on the ocean bottom. In this closer view, the magma rises and cools, forming new oceanic crust, widening the ocean floor, and spreading the continents farther apart. This area of rising magma is known as a mid-ocean ridge. Each movement in this animation represents approximately 1 million years. The Atlantic Ocean is growing wider, and North America is moving farther away from Europe, again at a rate of about 1 inch or 2 a year. This map shows where magma is surfacing between plate boundaries, creating a mid-ocean ridge system that circles the Earth. The ocean floor spreads in one direction on one side of the ridge and the opposite direction on the other. The mid-ocean ridge is where plates are born. Here's where plates die. In this drawing, the plate on the left is carrying an ocean basin and is moving in this direction. The plate on the right is also carrying an ocean basin, but is moving in the opposite direction. They are colliding. This is what happens when 2 plates carrying ocean basins collide. Again, each movement represents 1 million years. Pressures build until one of the plates dives beneath the other. The leading edge of the diving plate is consumed back into the Earth's mantle. This area where one plate is consumed beneath another plate is called a subduction zone. These pink lines mark subduction zones throughout the world. These are the areas where plate material is being consumed. The red lines again represent the mid-ocean ridge system where plate material is being generated. It is in these areas our Earth is continually changing. These dots mark the locations of earthquakes that have occurred in recent history. You will notice that most earthquakes occur directly above or near the mid-ocean ridge and subduction zones. In addition, earthquakes occur where two plates slide past each other. This is an area where two plates are sliding past each other. While California appears to be one piece, it is actually two. The western portion of California is riding on a plate that is moving in this direction. The rest of California is on another plate, moving in this direction. When sufficient pressure builds up between these two plates, one plate will suddenly thrust forward several inches, or even several feet. The devastating San Francisco earthquake of 1906 was the result of a major movement or slippage of these two plates. Scientists expect another big movement and another major earthquake in California at any time. Millions of earthquakes from now, as these two plates continue to move past each other, the western portion of California, including San Francisco and Los Angeles, will end up where Alaska is today. These symbols show the locations of active volcanoes throughout the world. Most volcanoes occur near the leading edges of moving plates, near the subduction zone. Here's how some volcanoes are created. The plate on the left is carrying an ocean basin. The plate on the right is carrying a continent. They are colliding. The plate carrying the ocean basin, because it is heavier, dives beneath the plate carrying the continent. As the leading edge of one plate is consumed beneath the other, some of the magma finds its way up between cracks and crevices in the continental crust. When the magma reaches the surface, the Earth bulges and pressures build. The result? The eruption of Mount St. Helens in 1980 was the direct result of plate subduction. Mount St. Helens is only one of many volcanoes in the Pacific Northwest. As this plate continues to subduct or dive beneath the plate next to it, more eruptions will undoubtedly occur, with devastation perhaps far greater than that experienced at Mount St. Helens. Like volcanoes and earthquakes, mountains are the result of plate movement. This map shows the great mountain ranges of the world. As you can see, most are located near plate boundaries. Here's how many mountains are made. In this example, the plate on the left is carrying an ocean basin. The one on the right is carrying a continent. They are colliding. As is always the case, the plate carrying the ocean basin, the heavier plate, will dive beneath the plate carrying the continent. The leading edge of the diving plate is consumed until there is a head-on collision between two continents. The continents squeeze against each other. Under the incredible pressure, layers of the Earth's surface are compressed and folded, rising high into the air. These raised layers of Earth are what we call mountains. The world's greatest mountain ranges, the Himalayas, the Andes, the Sierra Nevada, are still growing as pressures between two plates continue to push them higher and higher. These are young mountains. The Appalachian Mountains in the eastern United States are not growing. They're old mountains, and they are dying. The Appalachians were formed in a collision between two plates that occurred hundreds of millions of years ago. Those plates are no longer colliding, and since then, the Appalachians, once great mountains, perhaps as high as the Himalayas at one time, have been gradually worn down by wind and water. Let's go back in time. Even before there was ever a supercontinent called Pangaea. 500 million years ago, the world looked something like this. The continents are barely identifiable. North America is located here. Africa is way over here. Let's watch as the continents parade before us. First, the continents converge, creating the supercontinent, Pangaea. Dinosaurs rule the Earth at this time. Then the continents break apart, moving away from each other. They gradually approach their present-day positions. This is the world we know today, but it won't remain this way. The continents are continuing to move apart. Millions of years from now, the world may look like this. It will be a world much different from the one we know. These towering mountains will no longer be here. They will be ground to dust. Ocean waves will break on new shorelines. And pictures like this will only be ancient reminders of a world that once was.